Hi, this is Nikhil Soban Babu.
Hi, I'm Ujin.
Hi, my name is Ritarka, and I wanted to present our project on terrain traversability analysis with image dehazing. Just to give you a quick idea of what's going to be covered here, we're going to go over the motivation, the rugged, and the data set we used to train our model, some of the different dehazing methods we tried, and finally the objective accuracy measure, the segmentation of the GNF.
So, the motivation for our work is that terrain traversability analysis is a fundamental challenge in autonomous navigation, particularly for off road environments. Robots and vehicles must learn to evaluate the terrain to determine whether it's a navigable and safe path, which is crucial for applications like search and rescue, agricultural automation, and even for space exploration. However, environmental conditions such as haze, fog, or dust can significantly degrade the quality of visual data during inference, and this lack of clarity obscures critical terrain features like slopes, obstacles, or surface textures, directly impacting the accuracy of traversability analysis. Image dehazing is a vital pre-processing step to restore visibility and ensure that the downstream algorithms can make accurate decisions. Despite this importance, prior research in traversability analysis has majorly overlooked the effect of poor visibility during inference time. Particularly, these prior works use off the shelf datasets which are of high quality. However, during inference, the models that are trained on these high quality datasets fail due to poor visibility on the input image. So, by focusing on dehazing as a critical component of the pipeline, we aim to bridge this gap and enhance the reliability of traversability analysis in challenging environmental conditions.
So this is the rugged dataset, and we ran it through an image segmentation model, and you can see that it's able to detect the sky, the water, the ground very well. But what we wanted to do was that we had a lot of problem finding, excuse me, we had a lot of problem finding data sets where the images themselves were hazy. And so we tried a variety of methods, such as putting in a Gaussian filter, changing the color jitter or the saturation of the image. We found machine learning models online that would manually increase the supposed haziness of the image. And we randomized it immensely, so no two hazy images would look remotely the same. And this has the benefit of making our model much more resilient to real world fog or haze.
The dark channel prior is a powerful and efficient method to remove haze from a single image by leveraging statistical properties of natural scenes. The key idea of the dark channel prior is that in most natural images, at least one color channel has very low intensity in some non-sky regions. This forms what we call the dark channel. Using this principle, we can decompose a hazy image using the model shown in the slide, where I of x is the observed intensity, j of x is a haze-free image, the scene radiance, T is the transmission map, and A is the global atmospheric light. By estimating the transmission map and the atmospheric light from dark channel, we can recover the haze-free image. That is the entire idea of this algorithm. So the way the algorithm works is that first we compute the dark channel. This involves finding the minimum intensity value across all color channels in a local patch for each pixel. These patches capture areas of low intensity which are critical for estimating haze. And then the atmospheric light is estimated, where the bright pixels in the dark channel are assumed to represent the haze dominated regions like the sky. These regions are used to estimate A as the maximum intensity value among the top brightest pixels in the original image. Finally, the transmission map is estimated and it is also refined. And finally, the haze free image is recovered using the formula that is shown in the slide. So, after this, we wanted to conduct some ablation studies on the different features of this framework. First, we compared the effect of the patch size, which plays a crucial role in the haze removal. Particularly here, we see that a lower patch size is able to capture final details in the image, preserving texture and smaller features. However, the larger patch size provides a more smoother transmission map, causing losses in regions of complex textures, leading to poorer dehazing. We also compare the different refinement techniques of the transmission map. So here we see the first there is an original blurry image, and then we have compared between two different techniques. One is the guided filter and the other is the soft matting. Soft matting is reported to produce a very refined dehazed image. However, for the terrain segmentation task, we can see that the results produced by the guided filter and the soft matting are not significantly different. However, the inference time for them vary a lot. For the guided filter, it's 2.05 seconds, and for the soft matting, it's almost 10 times of the guided filter. So through this, we can see that for the terrain segmentation task, we can use other simple filters like guided filter for real-time performance.
So the next method we used is a CNN-based architecture for dehazing. The dehazing objective can be represented with this following equation, which is also called atmospheric scattering model, where J is a clean image that we want, I is a hazy image that our input, A is a constant for global atmospheric light, but often the highest intensity value in the image is used for this. And T is a transmission, the amount of light reaches to the pixel, and smaller value means higher absorption of light. T can be further detailed as a e to the negative beta dx, where beta is the scattering coefficient of the atmosphere, and d is the distance between the object and the camera. So, in the previous equation, from the previous equation, this can be rewritten as the following, which is basically you're combining the term T and A together. And at the end, K can be rewritten as the last equation written here. So previously in the traditional methods, there's algorithms such as DCP that estimated TX, and people often use statistical approach to find A. But now, there's a CNN-based architecture called AOD-NAT, which is end-to-end fully supervised CNN-based architecture, which tries to directly estimate this K term through the network. So instead of finding the T and A separately, the CNN-based architecture will basically automate the process of finding both of them terms combined, which we can use it to find the dehazed image. And by the way, the term K is also known as showing the depth and haziness of the pixels in the image. So the AOD-NAT, which is called all-in-one dehazing network. So in this network, there are 5 2D convolution network layers, which extracts low and high level features. And also there's concatenations to combine and preserve the features that those are extracted. And also value non-linearity layers to estimate this complex K-term. So these are some results we got from the baseline method and then also the other modifications we made. So in the far left plot or the image, you can see that at the top is the input hazy image, and at the bottom, you see the original image that we want to get, and in the middle is what the architecture predicted. In the baseline method, as you can see, the haziness didn't really dehaze. It's kind of dehaze, but it's really hard, still very hard to tell. In the second column, we try to change the learning rate and implement the scheduler, which were step and cosine annealing. So for the scheduler, we had to start with the higher learning rate compared to previously, since as the epochs go through, the learning rate will go down. The reason why we tried this scheduler was from the baseline method, we saw that the loss didn't quite go down after certain epoch. So we thought using different learning rate might help with that. And also we increased the batch size to see if there's the result comes out differently. And this was what we got in the second column. And there might be a little increase of the dehazing skill, but still can't really tell about that. And in the third column, we added the Laplacian loss combined with the MSE mean square error loss. We combine with the to the total loss together. And this idea was because in our segmentation objective, we are not like focusing on like small items, for example, like small birds or like small cup or glass. Rather, we are focusing on dividing the regions of sections as bumpy or like forbidden rough into a big regions of area. So Laplacian will help to identify the boundary in between. So that's why we brought this idea into our modification. And as you can see, there are some artifacts from this Laplacian. As you can see, some sharpness in the image, but we think that it brought the better skill in dehazing. Lastly, we added the residual part in the model, and I personally think this was the best result out of among these four. So in the residual part, we gave the original input to the K into predicting K. And this was to prevent any potential vanishing gradient problem and to have a better preserved data.
The next sort of dehazing method that we tried was the GAN. And this was we modeled our architecture based on IDC GAN, IDC GAN. And really the benefit of this was that IDC GAN was the previous work that helped remove rain from the images. And so using that similar architecture, we thought we could get very close to removing haze as well. One way we improved upon the original paper was using our dataset creation. In our original paper, they manually created and photoshopped images as training and test dataset. But since we used a much more automated process, our dataset was much larger and more than likely a bit, perhaps worked a bit better. And so you can see some images to the right. And you will notice that for some of these images, they come out crystal clear, especially if you take a look at this one. But for other images, especially the ones that were too blurry, it does not produce nearly as good as a result. And it shouldn't produce a good result, which is great. The last thing we want is for the model to hallucinate and create something that looks good but is in fact not actually true. So a bad image being produced by ultra blurry images is exactly the behavior we want.
So for the segmentation, which comes after the dehazing networks and algorithms, we use the model following called GNAP. So this GNAP architecture is rather segmenting on small, like very detailed items such as trees, birds, rocks. Instead, it kind of merge them together into a more coarse-grained segmentations, such as smooth, bumpy, rough, forbidden, obstacle, background, label regions. In at the beginning of the architecture, it used different size and scales to extract multi-scale features. And then since the outputs have a different dimensions, the smaller one will be chosen and by linear interpolation will be used to align their outputs. I think this is the most important part, excuse me, of this network, which is multi-head self-attention part. This learns different groups, like the safe, bumpy, forbidden groups, and it decides which area that each group needs to be focused on in the image. And it does it by learning the pixel and scale relationships. And it outputs A, which is calculated by the KQ and B values. And then it outputs P, the probability map for each group, using 101 convolutions and upsampling from the output A. And then the architecture uses these two losses. The first one is binary cross entropy loss for the group-wise attention loss. And then secondly, the cross entropy loss for optimizing the architecture. Lastly, the model uses MIOU and mean pixel accuracy to evaluate the segmentation result.
Hi, so this is the demo of our framework. So first here is the original image and here is the blurry image. So first we run the TCP and we get the output, and we run the CNN based AOT network and then we get the output, and we run the GAN, and then we finally, once we get all the results, we run the GNAF framework across all these images, and this is our final output image. So here we can see that segmentation that is created from the original and the GAN, even though the GAN is blurry, the segmentation is similar, and the DCP produces a very similar segmentation compared to the original image. However, the blurry image, the segmentation is totally off. However, with our dehazing frameworks, we can see that the segmentation is similar to that of the original image, which shows why dehazing is required during inference time and how it can improve the terrain traversability analysis. So finally, to compare performance, we use the MIOU metric. We use the same test split used by the GNF framework, and the MIOU reported on the original RUGD images is 88.64. However, for the haste images, we can clearly see that the performance drops to 32.24 of MIOU. However, with our dehazing frameworks and the three methods that we tried, DCP proves to provide the best MIOU of 82.50, and the GAN method gives 62.04, and the CNN based AONet method gives 70.73. However, even though the DCP method provides a high MIOU, the inference time for DCP is pretty high compared to the GAN and the AONet framework. So with this analysis, the AONet proves to provide the best results in comparison with the three frameworks.